We'll talk some throughout the year about organic compounds, which are compounds that contain carbon. They're the ones that we're really the most concerned about because of their effect on global climate change. Inorganic compounds we don't talk about a whole lot. There are a few that we'll talk about, but that's basically everything else. Cells we won't talk a whole lot about, but obviously, living things are made of cells, either eukaryotic or prokaryotic. Just as a refresher, eukaryotic cells are those that have a nucleus. Prokaryotic cells lack a nucleus. We'll also talk some about the macromolecules, which include proteins, lipids, nucleic acids, and carbohydrates. But generally speaking, we just talk about those in terms of how they supply us with energy and building blocks for our bodies. Matter can change in a couple of ways. It can be a physical change when it changes from a solid to a liquid, for example, or a liquid to a gas. Whereas a chemical change is where it's going to change from one chemical substance to another. So in this example here on the screen, you have carbon and oxygen reacting to produce carbon dioxide and energy. So that would be a chemical change. And one thing I want you to notice is what's known as the law of conservation of matter. And this particular equation is pretty simple because you've got one carbon on each side and two oxygens on each side. And so we didn't create nor destroy matter. So that's important to understand, that the matter we have is all that we have. It can change physically, it can change chemically, but we can't create nor destroy it. When we talk about the quality of matter, we're looking at a couple of things. We're looking at its concentration, how easy it is to get to, and how useful it is. So high quality matter is something that's going to be very concentrated. It's found near Earth's surface and has great potential for use as a resource. Low quality matter, on the other hand, will be dilute, meaning there's not a lot of it in the given space. It's often deep underground or dispersed in the ocean or the atmosphere, so it's difficult to acquire and usually has little potential use as a resource. So on this picture here, you have high quality versus low quality types of matter. So for example, the aluminum can versus the aluminum ore. The aluminum can is considered high quality because it's already been refined and made into a usable form of aluminum, whereas the aluminum ore is still in its raw form and has to be refined. So it's low quality as an ore, but high quality in the can. Now, energy comes in two forms, primarily kinetic and potential. So I'm sure you guys all remember potential energy is energy that's available to do work, whereas kinetic energy is the energy of motion. It's doing work. There are a couple of laws of thermodynamics that apply to energy. The first law of thermodynamics says that we can neither create nor destroy energy, so very similar to the law of conservation of matter. This is sometimes known as the law of conservation of energy. Energy is neither created nor destroyed, but it can be changed from one form to another. The second law of thermodynamics kind of looks at what happens to the energy as it changes form. So when energy changes from one form to another, some of that energy is degraded to lower quality, more dispersed, less useful energy. And that's usually in the form of heat. So as we see here in this picture, solar energy might be considered to be 100% in terms of its quality, like it's perfect. But as that is converted to chemical energy through the process of photosynthesis, some of that energy is lost as heat. And then when we eat the food that the plants made, again, some of that energy is lost as heat. And then when we use that energy that we gain from eating food to move, to think, to do life, more of that energy is lost as heat. So heat is considered waste energy because we can't really harness it and use it when it's lost in those transformations. So as with matter, we can talk about the quality of energy. It's basically how useful the energy is, how usable it is. And so high quality energy is going to be very concentrated and can perform a lot of useful work, whereas the low quality energy will be more dispersed and not very useful for doing work. So if we look at this chart here, it gives you a lot of different examples of low quality energy versus high quality energy. Geothermal energy is very dispersed throughout the ground, so it's a very low quality. Nuclear fission and nuclear fusion, on the other hand, have a tremendous amount of energy that can be harnessed, so very high energy quality. All right, real quick, kind of going back to matter for just a second, I wanted to talk about radioactive decay, which is another type of change in addition to physical and chemical changes that matter can undergo. And this is a nuclear change, a change in the nucleus of particularly isotopes. So some isotopes are unstable, and we call them radioactive isotopes. So carbon-14 that I mentioned earlier is a radioactive isotope. These spontaneously emit fast-moving chunks of matter called alpha or beta particles, or high-energy radiation called gamma rays, or sometimes both. And as it decays, what it's doing is it's changing into a different, stable, non-radioactive isotope. So we can measure the rate of decay, and it's called the half-life. And that's the time needed for half of the nuclei to decay into that new, stable, non-radioactive isotope. And so we can use that to measure the age of something. Sorry, guys. It can also be used to estimate how long a radioactive sample has to be stored before it's safe. So when we talk about radioactive elements that are used, like uranium, for nuclear power plants, we have to be able to store that until it's safe, and we need to know how long that takes. So the general rule of thumb is that it takes about 10 half-lives for something to be considered safe. A couple examples: iodine-131 has a half-life of 8 days, so it would take 80 days of storage before it would be considered safe, whereas plutonium-239 has a half-life of 24,000 years, so it would take 240,000 years for it to reach a safe level of radioactivity. Speaking of uranium, let's talk about nuclear fission for just a minute. The nuclei of certain isotopes with really large mass numbers can be split apart when struck by neutrons. And when that happens, a tremendous amount of energy can be released. And if you have a bunch of those nuclei, then when the first nuclei is split and energy released, you have neutrons that spread out and break apart other nuclei. More neutrons go out and break up more nuclei, and you get this chain reaction, which creates a tremendous amount of energy, which is how nuclear energy is produced. And so the trick is controlling that reaction so you don't end up with a bomb. So there are mechanisms that we'll talk about when we get to energy, our energy unit, where we'll see how they harness the energy but also control that chain reaction so it doesn't get out of control. And then on the opposite side of things is nuclear fusion. So nuclear fission is the splitting of the nucleus. Nuclear fusion is when two small nuclei are fused together. So typically you're going to use something like hydrogen, which only has the one proton and no neutrons. And when you fuse those two hydrogen nuclei together at extremely high temperatures, you get a heavier nucleus. And also a tremendous amount of energy. And this is actually the source of energy in the sun and other stars. So again, we'll talk more about that when we get to our energy unit, but the trick is the tremendous amount of heat required to do that makes it very difficult to do on a big scale to be able to harness it for electricity. But it is